In this short lecture, we're going to talk about brain and body growth in newborn infants. We're going to talk about the beginnings of motor development and how reflexes help to trigger motor development to occur. And lastly, we're going to talk about some of the patterns of sensory development in newborn infants. The Neonatal Behavioral Assessment Scale, or NBAS, is a standardized assessment scale that assesses infants on 28 behavioral and 18 reflex items. This is a standardized system that allows physicians to look at normal patterns of development. Because of the huge library of assessment data that we have on infants, we actually have a pretty good idea about what looks like typical or normal development and how much variation there is in those patterns. And it also tells us in what cases an infant might have abnormal development and what might be the potential causes. This NBAS assesses infants on their autonomic physiology. So are they able to regulate typical body functions, breathing, pulse rate, body temperature? Do they have typical activity levels and motor control? So young infants will mostly just have reflex control. Infants who are lacking in certain reflexes, that might be a signal that there's something wrong at the spinal cord or potentially in the brain with reflex control. So if an infant doesn't have some of the typical reflexes in their feet, that would suggest that there's likely damage at the base of the spinal cord. Sometimes this is caused by spina bifida. Spina bifida is a disorder that infants get when mom didn't have enough folic acid early in pregnancy. So this is usually folic acid that's present just as she gets pregnant or even a few weeks before she gets pregnant. Now, most foods are fortified with folic acid, so this isn't very common anymore, but it still does happen. In addition, physicians might be looking at whether or not infants have normal levels of alertness. Do they have typical patterns of sleeping? And then lastly, how do they interact with people? Do they make eye contact? Do they look away a lot? How long is their eye contact? Those are all the social systems of infants. Now, one of the most fascinating and important things that are happening to infants at this age is the change in physical stature, right? Newborns have a huge amount of growth. You can see here in the graph on the axis is height in yellow and weight in blue. So you can see that infants start at around 20 inches on average, and then by the first year they're up to about 30 inches, and by the third year they're up to almost 40 inches. So they've about doubled in height in just 3 years. This is one of the most rapid periods of growth that you'll see in newborns. And then they weigh around 7 pounds, 7 to 8 pounds. By the first year they're over 20 pounds, and by the third year they're over 33 pounds. And you can see here, this was my son when he was a newborn. This is around 3 months of age. And you can see not just the change in body structure, but also in facial structure. You can see that he's got more motor control at this point. This is him at around 6 months of age. You can see he can pick up his head and neck. He can't crawl yet, but you can see he's starting to get himself into the crawling position. This is him just over a year, so now he's walking. This is at 2 years of age. And then here he is at around 3 years of age learning to cross-country ski. So one of the things that's fascinating about infants is not just the change in body size and in weight, but also the change in their ability to be independent, right? Now, please realize that there are lots of physical changes that are happening and lots of psychological changes, but just because later on in development that physical change slows down or even stops, right? That doesn't mean that psychological changes have slowed down or even stopped. Okay, do not take physical change as necessarily an indicator of psychological change that's happening. Unfortunately, that was what a lot of early psychologists believed. Right? They believed that once children reach the age of 11, 12, 13, most of the important psychological changes have stopped. And as we'll see later in the course, there are some important psychological changes happening all the way throughout your lifespan. So one of the things that helps to get infants started off is what they're fed early in life. It used to be that that breastfeeding was what everyone did because it was the only thing that was available. Once in the 1950s we started to get bottle feeding formula available, moms suddenly had the ability to not have to breastfeed, and in fact for wealthier moms who could afford bottle feeding, they would actually prefer to bottle feed, and there was a stigma against breastfeeding in the 1950s. That has since reversed, so nowadays what we see is the opposite. Now there's stigma towards moms who bottle feed rather than breastfeed. How do you feel about this? What were you bottle fed? Were you breastfed? Now, longitudinal studies really don't show any big differences between bottle-fed versus breastfed infants. Bottle-fed infants are not less emotionally connected to mom. They're not more likely to be overweight. There may be some differences we see early on in life, but once you've moved a few years beyond the point where they're bottle feeding or breastfeeding, most of those differences disappear. Here in the green graph, you can see some of those short-term differences that happens in infants. So in blue is the prevalence of diarrhea, and in green is the prevalence of ear infections in infants who are either breastfed only, who receive mostly breast milk. About half of their calories come from breast milk, or everything is from formula. So what you can see here is that the more formula that infants are fed, the higher the rate of diarrhea and the higher the rate of ear infections. Those are short-term effects. Basically, once you get beyond the age where infants are consuming formula, those things disappear. So again, no longitudinal, long-term effects of bottle feeding, but there are some of these short-term effects. Again, because of artificial breast-like bags that infants can feed off of, dads can now actually gain some of the intimacy from breastfeeding because they can hold the infant in the same way. Or if you're not breastfeeding and you're bottle feeding, you can use those to actually get the same kind of connection. This is also true for same-sex parents. So two dads may be able to gain that same sort of intimacy, right, even though they might not be able to breastfeed. Okay, as infants get older, they'll become more picky, right? So by 6 months of age, they'll start to introduce food of other kinds into their diet. By around 2 to 3 years of age, because their growth is going to slow down, what you'll see is that infants slow down in their eating rate. Parents who continue to feed at a similar rate as what they did when they were an infant tend to get toddlers who are more likely to be obese. So be careful about how much you start to feed at 2 or 3. And it's pretty normal at this point because toddlers are starting to try new foods. They become pretty picky about what they eat. So they'll eat a little bit of various different foods. The best way to encourage toddlers to try new things is to give them a few limited number of choices in a very small amount. Let them try it in a way that it's on their own terms. They get to choose if they want to eat it. You don't force them to eat it because that actually usually gets the opposite reaction where they dislike that food. Instead, what you would do is you would continually introduce that food. One article that I read said on average it takes an introduction of a new food item 18 times before a toddler will start to like it, right? So just keep counting the days that you tried that new food item until eventually they start to eat it. And toddlers and children will remain picky, sometimes up through 9 or 10 years of age. So again, as you introduce them to new foods, you try small bits over time, repeatedly, without any punishment for not eating the food item. I was mentioning earlier that I wanted you to be careful about assuming that physical change in body was somehow indicative of other kinds of changes that are happening. This is actually called the principle of independent systems. This is the idea that each of your physiological systems develops at a different rate. So this is a comparison of the development of the nervous system in blue, the body system in green, or body size, and then sexual characteristics like development of breasts, the penis, other primary sex characteristics and secondary sex characteristics. So what you can see is that here on the bottom is their age. By 2 years of age, your infant has developed about 50% of their adult brain size. And we'll talk about what's exactly happening in that brain in just a minute. And you can see that by around the age of 10, they're almost at 100% of their adult brain size. Okay, so your brain system developed pretty early on. Whereas your body system actually has 2 periods of rapid growth, as you can predict. One of them is in infancy from 0 to 2, and then the other one is in puberty from around 12 to around 16 years of age. Those are the 2 times in your life when you have the most rapid growth. Otherwise, in the intervening years, you've got a pretty slow rate of growth. Then you've got development of sexual characteristics. So some of that happens early on, even before you've even been born. Some of the foundation that will become the external and internal genitalia has developed because of early hormone exposure. And then it'll basically turn off and it just sits there waiting until it's exposed to hormones later in puberty, which then it will start to develop at around the same time you'll get that pubertal growth spurt. Okay? But each of these is developing at a different rate and at a different time in development, so each of them is independent from one another. Let's talk about brain growth actually. So newborn brain development has three things that tends to be happening. Myelination. Myelin is this white substance you can see here on the screen. This is a picture of a motor neuron, and a motor neuron is what triggers muscles to move. Motor neurons have dendrites, these branch-like structures that take in information. So they take in electrical information if they're inside the body, or dendrites in the eye take in light information. Dendrites in your nose take in olfactory information or smell, and dendrites on your skin take in touch or temperature information. So dendrites are specialized to take in information. They convert it to an electrical signal that is actually sent down this long tube-like structure called an axon until it's converted into a chemical signal here at the terminal button. That chemical signal then is released and goes to a nearby neuron to then trigger, for example, muscle movement or a sensory stimulation, a sensory event, right? So you can see colors because of neurons sending signals and releasing chemicals. Well, this axon here that sends this electrical signal long distances. So when you want to send a signal from your brain down to your legs telling you to run because you see a zombie, for example, without myelin, actually, this signal is really slow. Think of this axon as something like a leaky hose, and it's got holes all the way along it. Okay, so imagine you're trying to get good water pressure down here at the end of this hose. Okay, well, because of the holes along the way here, this water pressure is very low. This signal quality is really low. Okay, well, this myelin, this cell here that's in white that wraps around the axon, is like duct tape around a leaky hose. It stops the leaking, and it actually allows the increased water pressure, in this case increased signal quality, to get to the end of these terminal buttons. Okay, that is not an exact description, right? That's not physiologically what's actually happening, but I wanted to give you something that's kind of an example of how you might think about what's happening. Well, myelin is actually starting to form once the baby's been born, and it continues to form throughout your life. So it speeds up and increases the processing of information. At the age of 5, infants have about 80% of their adult myelin, we believe. What that means is that your 3-year-old, when you yell at them to stop doing that, the time it takes for them to process that information, to understand, wait, what do you mean stop doing that? What does that mean? And then to figure that out is really slow. It may take 5 or even 10 seconds for them to realize what you're asking. So it's not that they're not listening to you. It's not that they're ignoring you. It's that they don't have enough myelin. It takes them physically longer to process information. So be a little bit more easygoing the next time you're around a 3-year-old. The other thing that's happening is that as your neurons are developing, you're actually born with a lot more neurons, brain cells, than you're ever going to use. Any of the neurons that are not getting stimulated, that are not receiving signals from nearby terminal buttons, will end up, you get rid of them. And you actually lose a huge number of neurons all the way through your life until you're at least 20 or 25. So your brain is essentially becoming very efficient at processing information, and you're losing neurons, and you're losing them on purpose, right? You're getting rid of basically all the excess. So you'll see that happening all the way through your adolescent life. The third thing that's happening is that initially what you have are lots of cells that are not connected to anything. So you've got a cell body here with maybe a few dendrites, but maybe it doesn't even have an axon yet. But as information starts coming into an infant's brain, that stimulation causes synapses to start to grow. So they start to branch out and grow more dendrites and grow more terminal buttons to nearby neurons. So you're getting more synapses, which allows you to process information. And in fact, a few post-mortem studies, people who have passed away, have shown that when you look at the brains of people who have special skill sets, for example, people who play stringed musical instruments, they actually have more synapses, more close connections between dendrites over here and terminal buttons of other cells. They have more synapses in areas of the brain responsible for touch in their fingers, right? And that makes sense. If you play a stringed instrument, you probably have to have very sensitive fingers and very fine motor control. So you're growing synapses the more you use those skills. Same thing for people who have gone to college. They tend to have more synapses in areas that are useful for vocabulary because they've probably been exposed to more words. Here is a demonstration of the number of synapses that are growing. These are actually not in humans, these are in infant rats. So these are newborn rats. You can see here's a cell body right here. Here's some dendrites, and there's an axon coming up here. Here's a little cell body right here, and just an axon, but not very well developed. By 1 month of age, you can see they've already started to grow lots of connections. By 3 months of age, these rats are continuing to increase. Here's 6 months, 15 months, and then 8, 24 months. So these are adult rats. You can see they've got very highly developed connections here already. So this is probably a similar process to what's happening in human infants and adults as they're growing more synapses and connecting their brain together. So when is this happening, right? When is all this growth happening? It's actually happening probably while your infant is sleeping. Newborns sleep on average about 16 to 18 hours a day. During this time, initially they'll have 4-hour sleep cycles. There'll be 3 hours of sleep, and they're awake long enough for a bottle, a diaper change, a little bit of mom or dad and dad, or mom and mom time, and then they're back to sleep again. That's probably also very beneficial for parents who, even though you may not want to sleep in 3-hour cycles, 3-hour cycles with only 1 hour being awake is a little bit more manageable than if they're awake continuously. By 3 to 4 months of age, they're in a 5 to 6 hour cycle. Okay, so they're up for maybe an hour and a half, then they're asleep for the remainder of that time. By 6 months of age, most infants are sleeping through the night, so they sleep for about 10 to 12 hours a day with about 2 naps during the day at some point. Again, there is some variability in this. Bottle-fed infants tend to sleep a little bit longer, sooner. Breastfed infants, because they don't get as full, tend to actually not sleep quite as well. They wake up more hungry. During this time, there are 2 stages of sleep, broad categories, stages of sleep that infants are in. They're either in non-REM sleep. REM stands for rapid eye movement sleep. So they're either in non-REM sleep or REM sleep. For newborns, about 50% of their time is in REM sleep. You can tell they're in REM sleep because their eyes will be moving back and forth very rapidly. You might think of it as dreaming sleep, so that's when most of your dreams happen. By about 12 months of age, only about 25% of that time is in REM sleep. What we believe is happening in REM sleep is a lot of that neuronal growth. A lot of those synapses are being formed. A lot of memory formation happens during REM sleep. So if you block someone from entering REM sleep, they're no longer able to form memories. Animals that don't enter REM sleep do not form long-term memories. So we think that REM sleep is forming synapses, and those synapses then help to form those memories. Non-REM sleep, on the other hand, seems to be the part of sleep where you're doing body growth and body repair. Release of growth hormone happens at that point. Release of healing compounds that help to regenerate cells. Protein construction is happening at that point. So non-REM sleep seems to be for physical regeneration, and REM sleep is for mental regeneration, if you want to think about it that way. The major risk of death for infants is sudden infant death syndrome, or SIDS. SIDS is a disorder caused when infants suddenly stop breathing while they're asleep. It's not very common. It is the most common cause of death, but for children under 1, only about 2 in 1,000 live births suffer from SIDS. Most commonly, it stops by the age of 12 months of age, as you can see here in the chart. Most infants who are going to have SIDS have it in their first 3 to 4 months of life, but there are cases where kids have died of what we suspect to be SIDS as old as 4 years of age, but again, very, very rare. What we think is happening in SIDS is that basically their medulla, their brain stem that helps to trigger their breathing reflex, isn't fully developed. So sometimes it just stops. Now, normally infants at this young age will wake up pretty frequently, right? So they only sleep in 2 to 3 hour shifts. During that time when they wake up, that triggers their breathing reflex to start all over again. But there are some things that may make it that they are less likely to wake up or less likely to re-trigger that breathing reflex. For example, low birth weight infants who have been born early tend to be more at risk for SIDS. Also, infants who have been exposed to carbon monoxide and cigarette smoke tend to be more likely to have SIDS. We think the carbon monoxide binds to their medulla, their breathing apparatus, so they don't form the normal reflex that triggers them to start breathing again. And then lastly, bottle-fed infants, because they tend to sleep longer in those first few months of life, are at a slightly higher risk. Again, very slight, but it is a risk for SIDS. The biggest risk actually used to be for infants who were sleeping on their stomach. In those first 3 months of life, infants cannot roll over. So if they're in heavy clothes and heavy blankets or a pillow in their crib and they were to sleep on their stomach, they would smother themselves in their pillow, and because they can't turn themselves over, they would die. It used to be SIDS before the 1990s was actually about twice as high, about 4 in every 1,000 births. It's lower now because the National Institute of Health started a back to sleep campaign to educate parents about keeping their infants until they can roll over on their own, putting them to sleep on their back, which has helped to reduce the risk of SIDS. The other thing that's happening in these early years is the development of voluntary motor behavior. Now, initially, infants basically are totally reliant on normal reflexes that have developed inside the womb. These reflexes are organized involuntary responses. They cannot really control them. For example, breathing. Infants automatically breathe when their mouth and nose is exposed to air. So that's why if you have a bathtub birth, an underwater birth, there is no risk for the infant to suffocate because they will not start breathing until they've been lifted out of the water. So as long as you keep them underwater, they won't start breathing and take in any water themselves. The other reflex they have is a sucking reflex. That sucking reflex is not very good, but it helps them to eat, right? In the first 2 weeks, most infants will actually lose weight if they're breastfed because they don't really know how to latch on to a nipple and feed successfully. The reason that infants put on body fat right before birth happens is to take into account the fact that they're probably going to lose weight as mom and baby are trying to figure out how to breastfeed successfully. Okay, so it's not something to be that worried about. If your infant starts to lose a little bit of weight, a few ounces in those first 2 weeks, that's pretty typical. So, but sucking helps the infant learn how to feed itself, and eventually that sucking reflex will disappear and it will become a voluntary motor behavior. Some other examples of reflexes infants have is the rooting reflex, which disappears again soon as they learn how to feed. The rooting reflex is where if you touch the side of their mouth, they'll turn towards that finger or nipple to feed. The stepping reflex disappears by about 2 to 3 months of age, and it helps locomotion. It helps them learn how to walk. So infants who get to practice that stepping reflex, so if you hold them above a solid surface or a carpet and their feet just barely touch the ground, you can see they'll start to walk. That helps them learn how to walk later. So infants who practice that stepping reflex more frequently will walk sooner. And if you don't want them to walk sooner, don't let them practice then. The Moro reflex is a falling protection. It's very common in many primate species. In humans, it disappears by about 6 months of age. It happens when they start to feel their head fall backwards. Their vestibular system, their sense of balance that's in their inner ear, activates, and it makes them think they're falling. So if you don't support the head of an infant and its head falls backwards, their arms will push out to the sides very rapidly and they'll start to cry. That's because they think they're falling. The arms go out to the side to help to grab something to stop themselves from falling. And in fact, actually in infant monkeys who are holding on to mom, the Moro reflex will actually stop them from falling out of trees and things like that. Lastly is the Babinski reflex. The Babinski reflex, whenever you put pressure on the bottom of the foot of the baby, it causes all their toes to splay outwards, to spread out. It gives them extra balance. It disappears by about 8 to 12 months of age, and again, we think it's for locomotion. We think it helps them to learn how to balance as they're walking. Remember, when you learn how to walk, you have to be able to put all of your pressure, all of your weight on one leg, and then lift up the other leg to move it forward. That learning how to walk probably is helped by that Babinski reflex. Now, what used to be that we would think of reflexes as being these automatically formed pre-existing neural connections. In fact, actually, evidence tells us that every reflex, even the ones that you're born with, like a sucking reflex, probably required practice. But that practice probably happened inside the womb. So it's these prenatal movements that actually allow those reflexes to form. Even reflexes need practice. How do we know this? Well, I'm going to take an example from fetal alcohol syndrome. This is a picture of an infant with fetal alcohol syndrome. You can see that they've got sort of the droopy eyes and the droopy mouth. These infants, because they were asleep in the womb, because alcohol, just like it does to anyone, makes infants sleepy. Infants who are exposed to alcohol in pretty high doses in the second trimester, so it takes about 4 cups of alcohol, 4 glasses of alcohol every day for the second trimester. So that's a bottle a day for all the second for 12 weeks. That's a lot of alcohol. So again, small amounts of alcohol will not damage the baby. A glass of wine here or there is not going to do anything to the infant. Okay, But in high doses, it basically causes the baby to sleep. And when they're sleeping inside the womb, they're not moving their face around. Because they're not moving their face around, we think they're not developing normal muscle connections. Those neurons, those synapses are not forming because they're not moving around. How do we know this? Well, the evidence actually comes from chickens. So you can actually look at a chicken egg, and when you shine a light to it, what you'll see is that chicks inside the egg are actually moving their head, they're pecking inside the egg. Okay? Well, if you take a small syringe and you inject into the egg a small amount of alcohol that mimics the amount that a fetus would be exposed to, the chicks sleep, just like other babies do, and they don't peck. When they're born, they do not have a pecking reflex, right? Normally all chickens are born with the ability to peck, and it helps them to feed themselves because they peck at any dark spot on the ground thinking it's something they can eat. Chicks who have been exposed to alcohol inside the egg do not know how to peck. They don't have the muscle strength in their neck to be able to peck successfully, and they cannot feed themselves, and they will die unless they're artificially fed. So evidence like this from chickens actually tells us that it's not necessarily that alcohol itself is causing brain damage, it's that it's causing you to sleep, which is not allowing you to practice those reflexes. Now, all of those motor skills, those basic reflexes we were just talking about, will work together. They will build on one another. We call this the principle of hierarchical integration. This is where your basic skills that you develop become integrated into more complex sets. That Babinski reflex, where your toes splay out to the side that helps you to have balance when you learn to walk, it was the first part of that gross motor skill. Now, there are lots of motor skills that are being developed. This is only a small sampling of them. And again, these age estimates are approximate because it depends on how often you practice them with your child and if they have other things going on that might inhibit them from developing some of these skills. Around 3 months of age, most infants learn how to roll over. By about 7 months of age, they have the core strength to sit alone. By 6 to 10 months of age, they're starting to crawl. And again, the sooner you practice with them, the sooner they're going to crawl. By 11 to 15 months of age, they're starting to walk. By 15 to 18 months, they'll have the quad strength and the core strength to walk upstairs. By 24 months of age, they can jump in place. But each of these actually builds. So crawling helps them to learn the back and forth leg movement that will become the foundation for walking, right? Where that back and forth leg movement. Sometimes parents are excited when kids, they skipped crawling and they went right to walking. That's actually not necessarily a good thing. Some evidence shows that children who never rolled over or never crawled actually overall develop poorer gross motor skills than children who did all of those sort of typical skills in the order as it's here. Some examples of fine motor skills that follow that same pattern. First, children get the open hand and reach and miss, right, where they start to coordinate, hand-eye coordination so they can grab things. By 10 months of age, they can grasp things with a thumb and finger. They can start to stack things by 11 to 15 months of age. And eventually, right, they can start to imitate strokes on a piece of paper and eventually copy a circle by about 3 years of age. And these, again, form the foundation for much more complex skills. The more practice you give your child with fine motor skills, buttoning things, tying shoes, even if they can't do it very well, it's the act of them trying rather than, for example, buying them Velcro shoes that actually is a good skill for them and is important for them to develop eventually. Okay? But realize that there are some differences in motor development. For example, the culture you come from really tells us that the amount of encouragement and practice alters the timing of motor development. For example, the Aki people of South America, they don't actually learn to walk until after 2 years of age. This is a picture of the Aki people here in South America. So why, you might ask? Well, so these infants are actually carried around for a long time, probably because of predator danger, right? There's lots of things, jaguars, snakes, that they have to be worried about. And so for the Aki people, they put them in a pack and they carry them around to delay walking. It's very easy for children to get lost in the jungles of South America. On the other hand, are the Kipsigi people of Africa. Their infants actually walk by 6 months of age because their parents actually have to be able to carry things, and so they don't have the ability to be able to carry them around frequently. So their infants are encouraged to walk on their own, and they'll walk by as early as 6 months of age. One of the other things that we develop eventually is the ability to determine depth. Some of you, if you have vertigo, you probably hate this picture right now, but this is not a skill that we initially have. Now, there are lots of things, lots of skills that go into depth perception. Part of it is binocular perception, right? So you've got two eyes that are coordinated together. Infants don't come out of the womb with this ability. In fact, their visual abilities is somewhat delayed. So initially at birth, they can see some high contrast colors like black, white, and red. By about 14 weeks of age, they have binocular vision, so now their eyes are starting to coordinate together so they look somewhat in the same direction. Your infants may still be a little cross-eyed at this point. They have pretty terrible acuity, visual acuity. So up until about 6 months of age, they really cannot see very well. At birth, they have 2200 vision, so things that are 20 feet away look like they're 200 feet away to them. So normally they can see around 18 inches in front of their face. So you have to be pretty close to their face for them to be able to pick out details. But infants are actually pretty sensitive to facial detection, and that's one of the first things they learn to recognize, probably because they're exposed to lots of faces. Okay, but again, exposure to toys like the one pictured here, in contrasting colors and things like that, doesn't necessarily speed up some of that process. Some exposure is good for infants, and it allows them to develop new visual skills, practicing using both eyes together and coordinating movements. By around 6 months of age, they'll have some depth perception, and they'll also have about 20/20 vision, if that's their normal vision. So it used to be that we were actually very concerned about the development of visual systems, because in ferrets and in cats, if ferrets or cats, if something happens to one of their eyes, they have a cataract, for example, that interferes with their vision, it seems to delay and disturb all of their visual development. So once a cataract forms in one of those animals, if you don't remove the cataract right away, the other eye that can still see continues developing, and that eye actually takes over all of the part of the brain that's responsible for vision, right? So normally what we'll do, for a long time, what we would do is, if an infant comes in with a cataract, for example, we'll actually cover up their other eye. We'll essentially keep it covered because we don't want that eye to start developing the visual system yet. Then what we'll do is, once the cataract's been removed, then we remove the blind, the eye patch, so that both eyes can start to develop together. And what we've always thought is that after a certain age, if within a few weeks you don't prevent that normal eye, that eye without the cataract from developing, that will damage their visual system for their entire life. This idea is something like a critical period, that there is a few-month window early in life for you to trigger visual development. And if something interferes with that process, if one of the eyes doesn't function normally, if it can't see, that the other eye will essentially take over the visual system in the brain, and that will disturb their ability to develop binocular vision, right? The ability to use both eyes coordinated together. So there's going to be a video link right below this video that will talk about new evidence that suggests that maybe there's not as much of a critical period as we used to think. Thank you very much. Email me with any questions.